In Module 7, we're going to begin to solve polynomial equations. Uh, what we've solved that's been most similar so far have been quadratic equations, which a quadratic equation is a type of polynomial equation. It's just one where the biggest exponent is a 2. Now, we might have third degree, fourth degree, fifth degree, where the exponents get bigger. So there's a couple things we have to understand in order to be able to do this. First off, is what you're going to be asked for. Okay, if you're asked for to find the zeros, the roots, the solutions, or the x-intercepts of an equation, there's subtle differences, but for all intents and purposes, we're going to consider these to be the same. Say find the zeros, find the roots, that just means to solve. Find the solution. Okay, now we have to understand the fundamental theorem of algebra. Fundamental theorem of algebra says that any polynomial function, regardless of whatever the degree is, has exactly n complex roots. We already learned that complex means that can be real or imaginary. So if I have a fifth degree polynomial equation, I'm going to be looking for 5 total solutions, 5 roots. If I have a third degree, I'm looking for 3 roots. But this includes multiple roots. You've previously heard of the concept of multiplicity. Sometimes you might have a solution that comes from a repeated factor, so it might count as more than one. So if you have a fifth degree, you might have 5 solutions, but one of those solutions might take up 3 of those slots or 4 of those slots, depending on how many times it's repeated. You also have to understand the types of roots. So we talked previously, the 3 types of roots, the 3 types of numbers that are probably the most important in Algebra 2 are rational, irrational, and imaginary. So the first ones we're always going to seek out are the rational roots. And the way that we're going to find them is by generating a list of candidates, generating a list of possible rational roots, and then testing each possibility, but through trial and error, to see which ones are actual rational roots. So the way you generate the list of possibilities is you get all the factors of the constants. Now, not every polynomial needs to have a constant, but whatever the lowest degree is, you would find all the factors of that number, and then you would take turns dividing it by all the factors of the lead coefficient, the number that's all the way out in front. Every polynomial has to have a lead coefficient. And then we're going to use synthetic division to now test each number. And what we're looking for, in order to be a root, what we're looking for is to get a remainder of 0. There would be using a remainder theorem for evaluation, and to plug in an input and get an output, and plug in an input and get an output. So what we're looking for is an output of 0. Up on the top of the slide, we talked about how the roots and zeros, they mean the same thing as kind of as an x-intercept. On a graph, an x-intercept is a point where you cross the x-axis, and on the x-axis, the one thing that every point on the x-axis has in common is that y is 0, that the output is 0. So I'm going to be using synthetic division to try to see if I get a 0 remainder, and if I do, then I know that that number that I plugged in is a root. Okay. Now, the other 2 types of roots, irrational and imaginary, what you need to know there is that something called conjugate root theorem applies, which means that if you're going to have any irrational or imaginary roots, they come in pairs. Irrational roots show up in the form of a radical, if you have a radical, typically a square root, and imaginary roots show up with an I. So if you're going to have any of those, they need to come in pairs. You're not going to have an equation that has only 1 irrational root or 3 irrational roots or 5 imaginary roots. They have to come in even amounts. That's what conjugate root theorem means. So the process that we're going to undergo, the steps for solving, is, as I said, we're going to start off with our rational roots. So we're going to generate a list of our possible rational roots by the method that we said in this in the slide before this. We're going to divide the factors of the constant divided by the factors of the lead coefficient. Now we're going to use synthetic division to test each one until I'm successful enough times to get my polynomial down to second degree, down to quadratic. So if I have a fifth degree polynomial equation, then I need synthetic division to work 3 times, because 5 minus 3 is 2. If I have a 7th degree polynomial equation, I don't think you're going to have many, but if you were, I would need synthetic division to be successful 5 times. If I have a third degree, I would need it to be successful once. I need to be able to get my polynomial down to quadratic, because once I'm down to quadratic, now I can use quadratic formula to find any roots that remain, which in many cases those roots are going to end up being either irrational or imaginary.